All right, so what if you've got a situation like this, where you need to know if this house is going to, or if this tree is going to fall and hit your house or not. Is it far enough away? In order to know that, you'll need to know how tall the tree is. But how do you measure how tall a tree is? I mean, you can't do that directly. You got to be able, well, good luck. You got to be able to do something different. Okay? And that's what we're going to talk about today, is how today is an extremely important day in terms of stuff that you actually could potentially use a lot. Hopefully, many of you are going to go on and do math stuff. I hope you do. I hope you go on and take math classes and go into engineering or economics or science or statistics or something like being an actuary. Or those are great jobs. They pay tons of money. There's a huge demand for them. But not everybody's going to do that. I recognize that. Even if you don't do that, even if you do something that is as far from math as possible, this is the kind of stuff today, and really I think all of it in Chapter 9, that's going to be extremely useful to you. If you are going to tile your kitchen floor, or if you're going to, who knows, you're going to roof your shed, or you're going to build a deck, or something like that, this is the kind of stuff that you use all the time. I use this stuff constantly if I'm doing projects. And maybe I could get by without it, maybe. But I guarantee if I tried to, if I didn't know how to do just a little bit of this, and I'm a math person, so I could probably do even more than this, but this isn't, if I didn't know how to do trig stuff, for example, this little right triangle trig ratio stuff I'm going to show you today, it would be so much harder to get the right cuts on those tiles. And I have tiled all our floors. If I wouldn't know how to, I wouldn't be able to get the angles right on the deck. You wouldn't be able to cut the hardy plank siding for the shed and all that stuff that you're going to pay people a ton of money to do if you don't do it yourself. And it's not hard. But this otherwise becomes very time consuming. And so this is very practical, real world, useful stuff to be able to do. What about this tree? Well, we're going to talk about this today. This is kind of, we won't get here for, half an hour, but we're going to be to a point relatively soon where you'll be able to answer that question. If you can do this, if you can just measure that angle, which you can do. Anybody can do that. All you have to do is just, if you had a protractor, you can just sight to the top of the tree and see what that angle is. Big deal. That's not hard to do. Anybody can measure that distance with a tape measure. So if you can get those two pieces of information, we can figure out how tall that tree is. We can do other stuff too. Now, I don't know if we'll get to this today. If not today, we'll do this on Friday. But what if you had something like, say, this? What if you... Dig it. Yeah. Stop. Okay, what if you needed to do this? What if you needed to, in the gables of your house, you wanted to do some decorative trim? So you wanted to cut some pieces that maybe did this kind of a thing. You're going to cut the planking so it matches that angle, right? So there's the pieces of planking that are going to join this way. But you got to know what kind of cut to make there on those. You got to be able to put that in your miter saw and know what angle to put your miter saw at. So how would you know? Well, you can do it pretty easily if you just have a little bit of trig. If you even knew what the pitch of the roof was, if it's a 412 pitch, or you could measure. I could make a little measurement there and find out what distance that is. Say I found out that when I go out 3 feet, I go up by, this is not to scale, but say I go up by 1 foot. Okay? And I want to know what kind of angle to make there. Well, I could just, if I could answer this question, if that's 3 and that's 1, and I want to know how many degrees is that to set my saw. Right now we can't do that, but we'll be able to do it shortly. I mean, this is what right triangle trig does for you. You can take ratios of sides in a right triangle and turn it into an angle also. Okay, so there's lots of stuff we can do with this. All right, now let's show you how. Okay, in order to do this stuff though, this trig ratios, we got to be able to orient ourselves in a right triangle. So All a trig ratio is a ratio of two sides of a right triangle. Okay? There are, trig is just short for trigonometry. There are three trig functions that we're going to, in case you didn't know that. If there are these three trig functions that we're going to be using, sine, cosine, and tangent, and those are abbreviated, like when you go on your calculator. You need your calculators to do this. You always look for these abbreviations. Sine, we abbreviate as SIN, cosine is COS, and tangent is TAN. But they mean those functions. Okay? All right, so that there are more of them that later on you'll deal with. And trigonometry, you probably have this idea in your mind maybe that trigonometry is hard stuff. Maybe you've heard people say that. And it can be pretty involved. There's a lot to it. We're not going to get into all the specifics and get into great detail with trigonometry this year because this is not a trigonometry class. This is a geometry class. But trig ratios, right triangle trig sometimes it's called, is really a geometry issue. Now if we wanted to get into real trigonometry, this is the kind of stuff that you'll be seeing when you take it. And it's very interesting and it's very useful. If I were to graph the function, y equals sine x on the xy plane, it looks like that. It's not like anything you've ever seen before. It just goes forever, just oscillates like that. It looks like an infinite wave. In fact, a lot of times it's called a wave train, and it's used to describe waves. Now, we're not going to get into that stuff now, but you can see maybe why this would be really valuable if you were going to study any kind of science or engineering, because waves are everywhere. I mean, most of what we experience in our everyday lives involves waves, even if you don't recognize that. When you look around and see things, well, light is a wave. When you hear things, sound is a wave. It's just everywhere. If you want to look at, you could look at actual waves too, ocean waves. If you want to look at how waves react to storms, or if you have all kinds of stuff. There's just limitless applications of waves. And if you really want to understand how waves work and use waves in math or in science, that involves trigonometry. Okay, so you're going to if you're going to go into those fields, you're going to do a lot more with this than what we're going to touch on today. But we're just going to hit this one little aspect of it. All right, so trig ratios. Now, this is how you remember your trig ratios. This is the old standby. If you can remember this one word, then you got it made. SOH-CAH-TOA. SOH-CAH-TOA says it all. SOH-CAH-TOA says this. What that stands for. I know that's a little odd, but everybody that's taken math for the last 80 years ends up, if you go through trigonometry or through right triangle trig, you learn that word, SOH-CAH-TOA. That's the best way. I mean, it's the most dependable, uniform way. It kind of does a little bit. I don't know. But you just got to be able to spell it. SOH-CAH-TOA. Okay. Yeah. Okay, here's what it means. The S stands for sine, the C stands for cosine, and the T stands for tangent. The three trig functions we just talked about. Now, what that tells you is what the ratio, the right triangle ratio is that tells us those quantities. So, for example, if I've got a right triangle like this, and here's angle A. Okay, right down there. There's vertex A, and so angle A is just the angle next to that. If I want to find the sine of angle A, then what SOH-CAH-TOA tells me is that the sine of A is equal to the length of the side opposite to A and the hypotenuse. Now, for angle A, wouldn't you agree that the green side would be the opposite side? Opposite meaning other side of the triangle, right? The opposite side is always going to be the side that the angle looks at across the triangle. H, the hypotenuse H, is always going to be opposite the right angle, right? And then the adjacent side, the adjacent leg, would be the blue one. Because what does adjacent really mean? If we say that two houses are adjacent to each other, what does that mean?
Next to.
Next to, yeah. Adjacent means next to. So this is the side, other than the hypotenuse, this is the leg that's next to angle A, right? And so we can always orient ourselves in the triangle that way. We know we've got an opposite, adjacent, and hypotenuse. And each of these three trig functions is just defined as a fraction, as a ratio of those side lengths, some arrangement of those side lengths. For sine, it's opposite divided by hypotenuse. For cosine, it's adjacent divided by hypotenuse. And for tangent, it's opposite divided by adjacent. That's it, right? And so what we're going to think of these sine, cosine, and tangent ratios as being is always, fractions. Okay. Let's take a quick example. What if I had this triangle? What if I had okay, let's call this one angle A and this one angle B. Okay. I want you to tell me what is the, just think about it, don't say it out loud. What's the sine of angle A? Okay, and let's remember, how do we spell SOH-CAH-TOA? SOH-CAH-TOA. Okay, that says it all, right? So sine of angle A, if we're talking about angle A, it's going to be what? Well, what's going to be the side opposite angle A? Which one? 3. Okay, so that's opposite. What's the hypotenuse? 5. What's the adjacent leg or adjacent side? 4. Okay, so what's my ratio then? Yeah, 3 divided by 5. That's it. That's what we mean when we say sine of angle A. It's that ratio. Okay. What's that mean? Just that. That's what it means. It's a ratio. What is the cosine of A? 4/5. Yeah. Cosine is adjacent, which is 4, divided by hypotenuse, which is 5. Okay. What's the tangent of A? Yeah, 3/4. Okay, now let's switch that around and let's talk about angle B. So if we're doing angle B, those are going to change, aren't they? Whoops. Yeah, sine. So what's the sine of angle B going to end up being? Say it again. 4 divided by 5, right? Does everybody agree now? Because from the perspective of angle B, and it's going to change for each angle, from the perspective of angle B, well, the hypotenuse always stays the same, doesn't it? Yeah. But the opposite of angle B is going to be this side, and the adjacent side to angle B is going to be that side, so it switches it around, right? Sine of B ends up being 4/5. What's the cosine of B? 3/5. And the tangent of B would be 4/3. Yeah. Okay, does that make sense? Okay. Questions on that? All right. So now I don't expect you. You still might be thinking, okay, yeah, but so what? I mean, what's the? And that's okay. Maybe you're even wondering, what is this? What are these sines and cosines? And to some degree, that's all I'm going to say about it, is there are ratios like that. Later on in life, you'll come to learn more things about them. But for now, if you can, there's the first benchmark step for us. If you can, in any right triangle, for a given angle, if you can identify the 3 SOH-CAH-TOA relationships, good. Yes, ma'am?
So obviously H is going to stay the same.
Right.
Is A and O going to stay the same on every triangle?
A and O will depend on which angle you're talking about. For angle B, that side is the opposite and that side is the adjacent. For angle A, it'd be different. For angle A, that would be opposite and that would be adjacent. Okay. Now you might notice that I haven't dealt with the other angle, the right angle. You don't. In right triangle trig, you wouldn't worry about finding the SOH-CAH-TOA relationships for a right angle because it really doesn't make sense to do that. What makes sense for us to do is to take the two acute angles and use SOH-CAH-TOA relationships for them only, not for the right angle. Okay? All right, so back to business. Okay, I want you to notice something then also about this. If we take these two triangles here, what can you tell me about those two triangles? Ah, they're similar. Okay. How can you prove it? You're right, but how could you prove that they're similar? What about them makes them similar? Okay. The ratios of the corresponding sides are all equal, right? The big triangle, all of the corresponding sides are exactly twice as big as the sides on the small triangle, right? So we get that scale factor of 2, and that's the hallmark of similar triangles, if the ratios are the same. So what can you tell me about angles A in both triangles and B in both triangles then? If the triangles are similar, in other words, what's true of their angles? The same, they're congruent. Right, okay. Now I want you to make a prediction for me. If we calculate, let's say, the sine of A in the top triangle, the big triangle, and the sine of A in the bottom triangle, take a second and just imagine that. Now, what's going to happen? I guess what I'm saying first of all is, are they going to be the same or different? Different? Very different. And the reason being because the big triangle is bigger. Right? Okay. And the side lengths are going to change. Yes.
They might be the same because you have 4 radius.
Oh, okay, but they might be the same because even though the side lengths are getting bigger, right, they're getting bigger proportionally. And so when I set up the ratios of the side lengths, maybe they'll end up staying the same. Now, something else I want to tell you that's maybe going to settle this for you. Maybe we can all come to the same prediction before we find out. We'll put it in the calculator to find out. Sines and cosines and tangents, trig functions, are functions where the numbers that we feed into the function, the input values, are always angles. So if I'm going to take the sine of a number, notice that even in our last examples, we always took the sines and cosines and tangents of angles, right? There's angle A, there's angle B. We said that the sine of angle A is equal to the ratio of opposite over hypotenuse. So in this case, it was A over B. Make sense? So you're always going to feed an angle into a trig function, sine, cosine, or tangent, right? Now, if I'm feeding the sine a certain angle, it's going to give me back a certain answer, which I'll demonstrate on the calculator in just a second. If I put in, for example, 25 degrees into a sine function, the calculator is going to give me a specific answer. There's only one answer that goes with that angle. Okay? So now going back to this next page, what do you think now? The sine of this angle A and that angle A, does that change your thinking just a little bit? Do you think they're going to be the same or different then? Yeah, are the angles the same? Angle A and angle A? Well, I thought they were. You guys told me they were because similar triangles have congruent angles, right? So maybe I should put that congruent sign in there. So if that angle is congruent to that angle, if they're the same, then isn't the sine going to have to give me back the same answer for both of those? If I put the same number into the sine, I should get the same number out, right? Agreed? Make sense? Well, that's right. That's the way it works. I'll demonstrate that. Look at these. Look what happens if we take these two triangles and we calculate all the trig functions for each, for the large triangle and the small triangle. Well, sine is opposite over adjacent, so that's opposite over hypotenuse, sorry. 8 over 17 in the big triangle, 4 over 8.5 in the small triangle, right? Well, if I turn those fractions into decimals, of course I'm going to get the same answer back, aren't I? Because those are the same ratios, right? Same thing for cosine. In the big triangle, cosine of A would be adjacent over hypotenuse, 15/17, which as a decimal is the same thing as 7.5 over 8.5, right? Get the idea? So the moral of the story then is that the trig ratios only depend on the angles. They don't depend on the size of the triangles at all. They just depend on what the angles in the triangles are. The ratios are always going to work out in such a way that it doesn't matter if the triangle is big or small. If they're similar triangles, the trig ratios will always be the same. Okay, so let's try one more of these. How about? Okay, I want to know. Okay, what's the? We'll say it out loud every so we get the same answer here. What's the cosine of A? Okay, what do you think? What's cosine of A? Okay, cosine. Let's spell it real quick first. Maybe that's always a good idea. How do I spell SOH-CAH-TOA? Okay. One more time. Now look at that spelling and tell me what's the cosine of angle A? Not 5. What do you think? I'll show you in a second. Yeah. 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 No, you can't do this one in your calculator. I'll show you in a second. Cammy. What about? So what's this? What are we going to do with this? Think about it. Get an answer for that. Talk that over real quick. Yes. Yes, you can. Yeah. I think this is recorded. I guess we'll see. 12/13. What about tangent? 5/12. Good. And what sine? 5/13. Okay. We got it. Okay, good. So next step. Question?
So whatever's on the bottom, besides the tangent or whatever, is always a hypotenuse?
Yep. You see? Because of the H there. Okay? Okay, so next step. Okay, yeah. How do we do this on a calculator? Did you send that back? On a calculator, how could we put in the sine of 74 degrees on a calculator? Okay. Yeah. Okay. Now you got to be careful with this. I'm going to show you something that, even though I'm telling you this, I can just about guarantee everybody is going to make this mistake that I'm going to warn you about, even though I'm warning you, because it's a real easy one to make.
I won't.
You don't think so, huh?
No, I will. I'm a magician.
Oh, true. Okay, so now look at this part right here. It says make sure that your calculator is in degree mode. What do they mean by that?
Degrees.
Okay, yeah. On your calculator. Okay, on your calculator, if you go to mode, look at the third line. The third line, you have a choice of radians or degrees. Now, those are both different ways of measuring angles. We can measure angles in radians. If we do that, if we divide a circle up into radians, it turns out there are 2 times pi radians in a circle. You're going to use that a lot, but you just haven't yet. We could also, if we choose degrees, how many degrees would there be in that whole circle? 360, okay. Now, which one are we probably going to stick with now? Degrees. We're familiar with degrees. That's a real, we have a pretty good idea. If we say a 60-degree angle, we all have a pretty good idea of what that looks like, right? So we're going to use degrees, but in order to use degrees, we have to make sure the calculator is set for degrees. So turn that, highlight degrees, and hit quit. Okay, then all we have to do, if I want to calculate the, what are we calculating? The tangent of 74, is I just go, notice I get these three buttons here, sine, cosine, and tangent. I'll just choose the tangent button, and then I'm going to put the angle in degrees inside the parentheses, so 74. And what that says is the tangent of 74 degrees. And your calculator is going to tell you that, and that's the answer. Okay, now, if you're going to use trig stuff then, and you're going to use sines and cosines and tangents, what that does mean is you're going to need a calculator. You're going to have access to a calculator to really make this stuff useful, because sines and cosines and tangents are not functions that nobody's just going to know. If I say, what's tangent of 74, nobody knows. Tangent of 74 is what the calculator tells you. It's not like some of the functions that we deal with in math. What if I gave you this function, f of x equals 7x minus 13, for example? If I needed to find out what the value of that function was when I plug in a number, I could do it without a calculator. I could just scratch it down on paper and do the arithmetic, right? And maybe if that had x squareds in it or something along that line, then that would make it more complicated. But I still could do it. Now, with trig functions, I can't. Trig functions don't work that way. Trig functions, the formulas that go with trig functions are so complicated that you just can't do them. You have to use a calculator. Okay? So we need a calculator to do this stuff.
Can we leave our calculator in the degrees?
Yeah, you might as well leave it in degrees mode. Absolutely. Yeah, that's the answer. That's the sine of 74. Right. Okay, so now why are we using this? Let's go back to the application of finding the height of the tree. How about? Okay, so and I guess we can take a quick look at this. This is one of the typical applications of trig. Probably the most common one is if you want to be able to find out how high something is, for example. The angle that's between the horizontal ground and whatever the point is that you're looking at, that's called the angle of elevation. So for example, in this case right here, here's the example we're gonna take a look at. 59 degrees would be the angle of elevation. We already described the situation, right? We want to know how tall this big tree is. If we get down here and measure the angle, we find out it's about 59 degrees. If we get out a protractor and sight to the top of the tree. And people that do surveying, when you see those guys with those, everybody's seen this, they put their little tripods up and they look through things.
Yes.
That's
what I'm annoying.
That's trig. What they're doing is they're using those little, they sight in on something and then it measures the angle real accurately. Okay, so that's really all they're doing is just a fancy protractor. But we don't need something quite that fancy. We can figure this out just by sighting on a protractor. We measured that we're 45 feet away. How do we find out the height of the tree? Well, it's really not that big a deal. Here's our right triangle, correct? Okay. Now, for the 59-degree angle that we've measured, what sides are represented by the 45 feet that we measured and the height that we're trying to calculate? So, in other words, this side is what in that triangle relative to 59 degrees? Opposite. Okay, so that's opposite. What about this one? Adjacent. Okay. So we want the SOH-CAH-TOA relationship that involves the O and the A, opposite and adjacent. Which one is that? Tangent, right? That's because if we write it out, there's opposite hypotenuse for sine, adjacent hypotenuse for cosine, and tangent is the one that has the O and the A, opposite and adjacent, right? So then how are we going to write out that trig ratio? The tangent of 59 degrees equals what ratio? Okay, so H is the unknown that represents the length of this side. That's the height of the tree, right? So we get H is the length of the opposite side. What's the length of the adjacent side? Okay. So now, how would we solve that mathematically? The unknown that we're trying to solve for is h. And we know by now really well that solving for a variable just means isolating. How do I get that h by itself? Yeah, multiply by 45. That's how I undo dividing by 45. So we get the answer h equals 45 times tangent of 59 degrees.
So do we just plug that into our
Plug it in our calculators. Now, when you see something like this, tangent of 59 degrees, that's a lot like the symbol pi. Tangent of 59 degrees is just a number, right? That's a number that your calculator is going to give you, just like your calculator will give you the number pi as I hit the pi symbol, right? So let's figure out what this is then. 45 times tangent 59 is 74.89, so it's about 75 degrees. I mean 75 feet, sorry, not degrees. 75 feet high, that's the height of the tree. Right?
That's how we could have did that one problem.
Yes. Right. It would have been easier with Trig. You're right, it would have been. Yep. Okay. Here's another example. What if we want to, let's say that we are going to climb up, we're going to climb a mountain. And we know, we look on our topographical map, and we see here's the mountain we're going to climb. To the top. Okay. We know, based on our topographical map, we know that we start off at an elevation of 8,000 feet. Okay? When we get to the top of the mountain, we're going to be at an elevation, we can see on the map that the top has an elevation of 12,200 feet. Okay? And furthermore, we can tell that this is a volcanic cone. And if we look at this thing in profile, when we're driving up to the mountain, we can just hold up our protractor, and we can see that the angle down here, this angle x, let's say, that is an angle of 60 degrees. Okay? If we want to know how far, if we walk straight up this thing, how far are we going to walk, how could we figure that out? Could I make a right triangle out of it and set up a ratio? Yeah, we can, can't we? Our ratio, I just have to kind of wrote this in a bad spot here, but what's that going to look like? What's our ratio if we make a right triangle out of this? Remember those numbers. So there's our right triangle, right? Now we said 60 degrees. We said that the bottom of this thing is at 8,000 feet. So what's the elevation gain between the top and the bottom? 4,200, okay? 4,200 feet, right? And what we're trying to find is the hypotenuse, right? How far are we going to walk? So we're going to call this distance, let's call that distance x, how about? See, that's the unknown. So what's the trig ratio we could set up then? Relative to this 60-degree angle, those are the two sides that I need. What are they? This one is the opposite, and this one is the hypotenuse. So what's going to be the SOH-CAH-TOA relationship with an O and an H? Sine. Huh. So sine of 60 equals what ratio? Okay, so that's going to be 4,200 divided by h, which is x, right? What we're looking for. Okay, now how do I go about solving that one? Okay, I could multiply by x, right? Another way of thinking about it is sine 60 is the same as sine 60 over 1. If I write them as ratios, then what could I do? Cross multiply, same thing, isn't it? If I cross multiply, I'm going to get x times sine 60 equals 1 times 4,200. And then now what to get the x by itself? Divide by that number. That's all it is, the number sine of 60, right? Okay, so okay, and then the numbers cancel, and I get my answer. X equals 4,200 divided by sine 60. And what's that give us? 4,800 to the nearest foot is 4,849? Okay, 4,850 if we round to the nearest foot. So that's how far we could expect to walk up that steep mountain. We're actually going to walk a distance of 4,850 feet. Okay? Make sense? All right. Yeah, good. Okay, that's where we'll hold off for today then.